New Mexico, July 16, 1945. The night is silent, except for the ticking of a stopwatch. A 100-foot steel tower rises in the desert, holding a device no human has ever used before. At 5:29 a.m., the countdown ends. A flash brighter than the sun turns night into day. A shock wave rolls across the desert floor. The sand fuses into glass. It's the birth of the atomic age, the Trinity test. But before that button was pressed, some of the greatest minds in physics had one terrifying thought. What if this bomb doesn't just explode? What if it ignites the atmosphere itself? In 1942, long before the test, theoretical physicist Edward Teller raised a chilling possibility. He wondered whether the intense heat from a nuclear explosion, millions of degrees, could cause nitrogen in the air to fuse together. If that reaction somehow spread, it could set off a chain reaction across the atmosphere, turning the entire sky into one giant thermonuclear fireball. Translation: if he was right, pressing that button could end not just the war, but the world. That fear wasn't just science fiction. It reached all the way up to J. Robert Oppenheimer, the project's leader, who personally asked Arthur Compton, "Could we destroy the atmosphere?" The team ran the numbers again and again. They even wrote a classified paper, Ignition of the Atmosphere with Nuclear Bombs. The verdict? Mathematically possible, but physically impossible. Still, that's not exactly comforting when you're seconds away from lighting the desert on fire. To ignite the atmosphere, the explosion would need to trigger fusion reactions in the gases around us, mainly nitrogen, 78%, and oxygen, 21%. But here's the key. Fusion requires extreme conditions, the kind found in stars, not air. Inside the sun, gravity crushes hydrogen atoms together under unimaginable pressure, forcing them to fuse. On Earth, the air is far too thin for that, even at the center of the Trinity fireball. With temperatures over 100 million degrees Celsius, the pressure and density drop instantly as the blast expands. The air cools faster than any fusion reaction could spread. That's why fusion bombs, the later hydrogen bombs, needed a separate fission trigger and a confined fuel capsule to hold the reaction in place. The open sky simply can't do that. As Hans Bethe, one of the project's top physicists, later said, "The densities are too low. The air cannot sustain a chain reaction." In simpler words, even if a few nitrogen atoms fused in that first instant, the reaction would die before it could move a millimeter. Let's imagine, somehow, Teller's nightmare came true. The bomb triggers runaway fusion in the air. Within seconds, the nitrogen in the sky begins to burn, releasing energy billions of times greater than any weapon ever built. The atmosphere itself becomes fuel. Temperatures rise to tens of millions of degrees. Oxygen burns out. The shockwave travels around the Earth in seconds. The oceans boil. The sky glows white. And within minutes, every living thing on the planet is gone. Even the surface rocks begin to melt. The Earth turns into a glowing ember in space, our final act of self-destruction. It's an apocalypse that ends before anyone has time to realize it began. But that didn't happen. Why? Because the universe has rules, and physics said no. The calculations, checked and rechecked by Konopinski, Teller, and Bethe, showed that even at 100 million degrees, the energy produced by any brief fusion in the air would be instantly lost to radiation and expansion. In other words, the heat couldn't build fast enough to sustain itself. And here's the most important proof. Since 1945, humanity has detonated over 2,000 nuclear weapons, including hydrogen bombs, 3,000 times more powerful than the one at Trinity. None of them ignited the atmosphere. Not one. The same physics that protected us in 1945 still holds true today. Even without global ignition, the Trinity test was a turning point in human history. The blast yielded the power of around 21 kilotons of TNT, vaporizing everything within hundreds of meters. Temperatures at ground zero reached over 10,000 degrees Celsius, melting sand into green glass. later called trinitite. The shockwave shattered windows up to 160 kilometers away. The mushroom cloud climbed 12 kilometers into the sky. Fallout particles drifted over 48 states, though few understood the radiation risk at the time, and Oppenheimer's famous words came to mind: "Now I am become death, the destroyer of worlds." Except the world, thankfully, didn't end. The what if wasn't pointless paranoia. It was a reminder of humility. For the first time, humans had built something powerful enough to challenge the stability of the planet itself. The question, could we destroy everything, wasn't science fiction. It was physics, pushed to its absolute edge. And even if the math said safe, every scientist there knew if the math was wrong, they wouldn't live long enough to find out. That moment, that risk, became the moral shadow of every nuclear weapon since. Because while the atmosphere didn't ignite, something else did. Our understanding that humanity now held the fire of the gods, and no guarantee we'd use it wisely.